It is just past 3 in the morning on a wet grade somewhere in the mountains, and a loaded freight train has stopped moving. Not stopped exactly. The locomotives are still working. You can hear them straining, the exhaust hammering against the trees. The driving wheels are turning. They are simply turning in place, spinning against the rail, throwing a thin curtain of sparks into the dark, while 11,000 tons of train sits perfectly still behind them. The engineer does not add power. Adding power would make it worse. Instead, he reaches for a small control and releases the cheapest material anywhere on that locomotive: sand. A narrow stream of it drops onto the railhead a few inches ahead of the wheel. Within a second or two, the spinning stops. The wheels bite. Couplers stretch one by one back through the length of the train, and the whole thing begins to crawl uphill. Here is what makes that worth thinking about. The locomotive that just needed help is a modern machine. It carries microprocessors that sample wheel speed hundreds of times per second, software that models the entire train, and a control system sophisticated enough to run without a human hand on the throttle for miles at a time. And the thing that saved it was a mineral that was old before the first vertebrate crawled onto land. Every mainline locomotive on Earth carries sand, not as a backup. As a primary system, plumbed and pressurized and refilled on a schedule, taking up space and weight that engineers would love to use for something else. The technology has been on locomotives since the 1840s, and it has never been replaced. So why does an industry that moves a third of a continent's freight still depend on a bucket of crushed quartz? And why, after nearly 2 centuries, are railroads now spending serious money trying to use less of it? To answer that, you have to shrink down, way down, because the entire drama of railroading happens inside an area smaller than a postage stamp. Put a steel wheel on a steel rail and load it with tonnage, and the two surfaces do not really touch across any meaningful area. Both are hard, both are curved. They deform against each other just enough to form a tiny oval of genuine contact, roughly the size of a fingernail, and everything the train does has to pass through it. All the pulling, all the stopping, all the steering. On a heavy freight car, tens of thousands of pounds are pressed through a patch you could cover with a thumb. That patch is the reason railroads exist. Steel rolling on steel is astonishingly efficient. There is almost no deformation, almost no squirm, almost nothing wasted. The whole economic case for rail comes from that hard, slick, low friction interface. And that is exactly the problem. The same slickness that lets a train roll forever also means the wheel has very little to hold on to. Railroaders call the available grip adhesion, and they measure it as a fraction of the weight sitting on the driving wheels. On clean, dry rail, older rules of thumb put it somewhere around 1/4 to 1/3. Wet it down and it can fall toward 1/5. Add a film of grease, a smear of oil from a passing car, frost, drizzle after a long dry spell, and it can collapse below anything usable. That number is not an abstraction. It is a hard ceiling on the train. A locomotive can only pull as hard as its wheels can hold. Build an engine with more power than its weight can transmit, and all you have built is a very expensive machine for polishing rail, which is why, from the beginning, the fastest way to buy grip has been to put something gritty in that contact patch. The earliest solution was exactly as crude as you would expect. A fireman or a brakeman climbed down with a bucket and threw sand on the rail by hand, sometimes walking ahead of the locomotive, scattering it where the grade steepened. It worked. It was also slow, dangerous in traffic, and completely useless once the train was already moving. The obvious fix was to carry the sand on the locomotive and drop it where it was needed. In 1841, an ironworks owner from New York named Jordan Mott, a man better known at the time for inventing a stove that could burn anthracite coal, patented a small funnel-shaped box that poured sand onto slipping driving wheels. Mott preferred to drop it on the wheel itself, but in his own patent language, he noted almost as an afterthought that it might work just as well aimed at the rails ahead of the wheels. He was describing the method every locomotive on the planet uses today, and he does not seem to have been particularly convinced by it. For the next 40 years, sanding was a gravity business. A box sat above the drivers, a pipe ran down toward the rail, a lever in the cab opened a trap, and the sand fell. Simple, and in a crosswind, close to useless. Sand dropping several feet through moving air does not land where you aimed it. Crews watched their traction blow sideways into the ballast on exactly the exposed windswept stretches where they needed it most. The fix arrived in Britain in 1886 when an engineer on the Midland Railway developed a system that used a jet of steam to blast sand horizontally out of a nozzle directly into the gap where wheel met rail. Now, the wind did not matter. The sand arrived under pressure, precisely placed in the exact spot where it could do work. The effect on locomotive design was immediate and a little strange. Locomotives with a single pair of driving wheels had been falling out of favor because a single axle simply could not put enough weight down to grip. Steam sanding changed that math. Within a year, British builders were producing elegant single-driver express engines again, and they kept building them for another decade and a half. A better sandbox brought an entire extinct class of locomotive back from the dead. American practice went a different direction, and the reason is worth knowing, because it explains the shape of every steam locomotive you have ever seen in a photograph. There are usually two domes on the boiler. One of them, the steam dome, collects dry steam. The other one, often ahead of it, is a sandbox. Builders put it up there deliberately, straddling the hottest large object on the machine, because sand only works if it is bone dry. Damp sand does not flow. It bridges, packs, and plugs the delivery pipe, and a plugged sand pipe on a wet grade is worse than no sand at all, because the engineer is counting on something that is not coming. That single requirement, dryness, drove an entire support industry that most people never notice. Large terminals ran drying houses, small buildings where wet sand was spread, heated, screened, and stored. In British engine sheds, sand stoves worked through the night so that every locomotive could be topped off each morning with sand that would actually run. When steam gave way to diesel, the coaling towers came down, but the sanding towers went up in their place and remain there today. Tall silos beside the servicing tracks with hoses hanging down. And the person filling the boxes is doing a job that has barely changed in a century. Climb up, open the fill hatch, fight a heavy hose, take a face full of silica dust, move the locomotive, do it again for the next box. A road unit may carry a ton or more of sand split across boxes at each end, and it gets checked every time the locomotive is serviced, because a unit that goes out with empty sand boxes is a unit that will stall somewhere expensive. Which raises a question worth pausing on. If it is just sand, why does any of it need to be special? It is not just sand. Traction sand is a specified industrial product, and the specification is fussy. It wants to be almost pure silica, because quartz is hard, around 7 on the mineral hardness scale, hard enough to survive being crushed between two pieces of steel rather than simply turning to dust on contact. It wants angular grains with sharp edges rather than the smooth, rounded ones you would find on a beach, because sharp corners bite. It wants a tightly controlled grain size, typically a fraction of a millimeter to a millimeter or two, because grains that are too big jam in the nozzles and grains that are too fine cause a problem we will come back to shortly. And it wants moisture down around 1% or less, washed free of clay and organic matter, screened, dried, and kept that way. Get any of that wrong and the system either clogs or quietly stops working. If you are enjoying this, subscribe. We cover locomotive engineering and railroad history every week. Now, the moment itself. A grain of sand leaves the nozzle in a jet of compressed air, travels a few inches, and lands on the railhead just ahead of an oncoming wheel carrying something close to 18 tons. What happens next takes microseconds. The grain does not roll out of the way, and it does not survive intact. It is caught, driven into the interface, and shattered. What forms is a thin layer of crushed quartz fragments trapped between wheel and rail. Engineers call it a third body layer, and it is doing two jobs at once. Its fragments are hard enough to key into both steel surfaces, resisting the sliding motion that makes a wheel spin, and it is scouring, abrading away whatever film was on that rail in the first place. The rust, the oil, the water, the greasy residue of 1,000 passing wheels. The sand does not simply add grip. It cleans a path to the steel. That is the beautiful part. Here is the part that surprised the engineers. Sand is not always the answer. Under certain conditions, sand makes things worse. Laboratory work over the past 2 decades has shown something counterintuitive. On rail that is already dry and clean, feeding in a heavy dose of fine sand can actually reduce grip. The crushed grains form a layer of loose powder that behaves less like grit and more like a solid lubricant, a bed of tiny ball bearings between wheel and rail. More sand, less traction. The people who spent a century assuming that more was always better were, in a narrow set of conditions, wrong. And then there is the failure mode that genuinely frightens signal engineers. On enormous stretches of railway, the way the signaling system knows a train exists is disarmingly simple. A low voltage electrical current is fed through the rails. When a train enters that section, its steel wheels and axles short the two rails together, the current path changes, and the system registers the section as occupied. That is what turns signals red behind a train and keeps another one from following it into the same piece of track. The whole arrangement depends on wheel and rail being in solid electrical contact. Sand is quartz. Quartz is an insulator. Pack enough crushed quartz into the contact patch and you can, in principle, lift a train's wheels out of electrical contact with the rail it is standing on. The signaling system stops seeing the train, not as an obvious fault, which would fail safe, but as an empty section of track, which does the opposite. The industry calls this a wrong side track circuit failure, and it is precisely the kind of quiet, invisible fault that safety engineers lose sleep over. Confirmed cases are rare, but the risk is real enough that the amount of sand a modern train may drop, and how quickly, is a regulated quantity rather than a matter of taste. Sand is essential. Sand is also a hazard. Nowhere is that tension clearer than in autumn. Everyone has heard the joke about leaves delaying trains. The joke is based on a misunderstanding. Loose leaves on the track are harmless. The problem is what happens after a few thousand tons of train have rolled over them. Under that pressure, the leaf matter is crushed, chemically reacts with the iron of the railhead, and bonds into a thin, hard black film. It is not debris sitting on the rail. It is bonded to it, and it does not brush off. In damp conditions, morning dew, drizzle, light frost, that film becomes extraordinarily slippery. Measured friction can drop to a small fraction of what dry rail provides. Now, the sand is not about pulling, it is about stopping. On the evening of the 31st of October, 2021, a passenger train approaching a junction near Salisbury in southern England could not stop. The driver braked, the wheels locked and slid. The train passed a red signal and struck the side of another passenger service crossing ahead of it, and both trains derailed into a tunnel. Investigators found the adhesion at that spot was very low because of leaf contamination on the railhead, made worse by a band of drizzle that had passed through just before the train arrived. More than a dozen people needed hospital treatment. 11 years earlier, another British train had failed to stop at a station and ran for well over 2 miles with the emergency brake applied the entire time. The investigation concluded there had almost certainly been no sand in the hoppers at the leading end of the train. Empty sandboxes. That was the difference. In the years since, operators have been fitting equipment that can vary the sand feed rate rather than dumping a fixed amount, tuned to deliver more when the wheels are sliding and less when they are not, precisely because both too little and too much carry a cost. And that cost is not only measured in accidents. Every grain of sand that does its job leaves damage behind. Quartz driven between two steel surfaces abrades both of them. Sanding accelerates wear on wheel treads and railheads, and heavily sanded territory needs grinding and replacement sooner. The sand that misses, and most of it misses, does not vanish. It falls into the ballast, the crushed rock that holds the track in place. Ballast works because it drains and because its stones interlock. Fill the voids with fine sand and it drains less, holds water, and needs cleaning or replacement. Railroads pay for that sand 3 times, once to buy it, once in wear, and once to dig it out of the track, which is why the modern answer is not more sand. It is smarter sand. Look at what a current locomotive actually does. It measures the speed of every axle continuously and compares them. A wheel set that starts turning slightly faster than the others is beginning to slip, and the control system can see that long before the crew hears anything. It then does something that sounds backward. It deliberately allows a small, controlled amount of slip, because a wheel creeping fractionally against the rail actually generates more pull than one gripping perfectly. It rides that edge, trimming power axle by axle thousands of times a minute. Sand still gets applied, but it gets applied by the computer in measured amounts at the specific wheels that need it for as long as they need it. Sanding stopped being a lever the engineer pulls and became one more variable in an adhesion budget. Modern traction systems have raised the usable adhesion of a locomotive dramatically. They have not eliminated the need for sand, and nothing on the horizon suggests they will. Every ceramic, every gel, every friction modifier that has been tried has to answer the same 3 questions that crushed quartz answered in the 1840s. Does it grip? Does it flow when it is cold and wet and 3 in the morning? And does it cost almost nothing? So far, nothing else answers all 3. The next time a freight train rolls past you at a crossing, look at the bottom of the lead locomotive, just ahead of the first wheel. There is a small metal pipe there, angled down toward the rail, ending a couple of inches above it. It is not glamorous. It is not in any advertisement. There is no software in it, but everything above it, the engine, the alternator, the traction motors, the entire 4,000 horsepower argument for why trains beat trucks, is worth nothing at all unless that pipe can put a few grains of sand in exactly the right place at exactly the right moment. The whole railroad rests on a patch of steel the size of your thumbnail. And for nearly 2 centuries, the way we have made that patch hold has been to fill it with the oldest, cheapest, most ordinary material on the planet and let the weight of the train do the rest.